Hey guys, welcome back to Pop 'em Up Chem. In this video, we're going to be picking up where we left off with nucleophilic substitution. We want to develop the ideas for the HL students, and we're going to have a look at some other factors that affect the rate and some other nucleophiles. So, quick question just to get you started. What is the IUPAC name of this compound? Pause the video to give yourself a moment for that. Awesome. So if we draw this compound out, we can see that telltale COOH. We're going to have 3 carbons with the double bond O and the OH, which of course is a carboxylic acid. We've got 3 carbons, so it's going to be propanoic acid. Before we get stuck in then, quick recap. For SN1 reactions, we usually require a tertiary halogenoalkane because a tertiary halogenoalkane allows the heterolytic split of the polarized bromine in this case, but it could be any other halogen bond, which allows the formation of the carbocation intermediate. That carbocation intermediate then reacts with the nucleophile, which attacks the carbocation and therefore substitutes in the position that the halogen was at the beginning. SN1 because it only has 1 molecule in that slow rate determining step. In SN2 reactions, we usually have primary, and that's because we don't have a stable carbocation intermediate, no positive inductive effect. So we instead form this transition state anion as the nucleophile attacks, backside attack, and we have these 2 long range bonds by both the halogen and the incoming nucleophile. Then after a little period of time, the bromine leaves, leaving minus HBr, and leaves us with our alcohol. So what factors actually affect the rate of a substitution? Well, we've already looked at the mechanism because of the stability of the intermediate carbocation. We'll have a little look at that because steric hindrance and the solvent can also affect it, as well as we're going to look at the leaving group and the nature of the nucleophile, although we're not going to go into too much depth about the nucleophile. So for SN1, remember the rate is equals to K times the concentration of the halogenoalkane, whereas for SN2 we have the rate is equal to K times the concentration of the halogenoalkane, also times the concentration of the nucleophile. This means that if we consider all things were stayed the same, similar molecular masses, temperature, concentrations, then the SN1 reaction is going to go faster because it relies on less components, and so therefore molecules that favor SN1 reactions will generally have a faster rate. So tertiary generally go SN1, so they generally have the fastest rate of reaction, and primary generally go SN2, so they have the slowest rate of reaction. That's obviously just a general trend. As I've already discussed in the previous video, the mechanism is really affected by the stability of the intermediate carbocation. Because an SN1 reaction requires that heterolytic break of that halogen bond to form the carbocation, there needs to be substituent groups on that carbon that was bonded to the halogen that are able to donate electrons and give that positive inductive effect that will stabilize that carbocation. So the more stable that intermediate carbocation, the more likely an SN1 mechanism is likely to occur. But that's not the only factor at play. We can also have steric hindrance, for example. On a fundamental level, steric hindrance is simple. It just means that there are things that physically get in the way of an attacker. So if we have the halogenoalkane with substituent groups, if we think about these groups as huge regions of electron density, remember a nucleophile is going to have a negative charge. And so it wants to come through these big clouds of electrons that these R groups, any substituent group has, and so these can block the attack of any potential nucleophile. Thus, the less substituent groups we have, the more likely it is that the nucleophile is going to be able to attack, because it doesn't have to try and get around these groups. Another reason why primary favour SN2. If you look at the word steric, which looks similar to the word stereo, then you can kind of get an idea here. For the music producers among you, you'll know that stereo gives a sense of presence. When we mix music in stereo, it means that you have a left and a right hand panning to the left and to the right. And that gives a sense of space. And so steric comes from the Greek, which means solid object or three-dimensional object. So we're talking about things in 3D here. The last thing that can affect the mechanism of the reaction is the solvent that we use for the reaction to occur in. So there are two types of solvent. We have protic solvents and aprotic solvents. And really, they're kind of like what they sound like. Protic solvents can easily donate or provide H+ to the reaction, and aprotic solvents cannot donate H+. So protic solvents can form hydrogen bonds and, of course, donate protons. This means that they're actually very good at dissolving salts, thinking back to the polarity of ions being able to easily dissolve. And this is pretty much most solvents that you would commonly know: water, ethanol, ammonia, carboxylic acids, etc. Aprotic solvents are quite simply the opposite. They can't do these things and are usually organic solvents, and although they can be polar in nature, they're not going to form hydrogen bonds. Aprotic solvents usually encourage SN2 reactions because they don't aid the stability of the carbocation intermediate as the protic solvents do, which, as we know, is required for the SN1 mechanism. Beyond the mechanism that we've looked at for the reaction, we can also look at the leaving group, or the halogen. So the nature of the halogen is going to determine how much that halogen wants to come off of its carbon-hydrogen bond, and we usually look at chlorine, bromine, and iodine for this. So the thing that makes a good leaving group is effectively the ability of that leaving group to form a negative charge with itself, because we can think of leaving groups as nucleophiles in reverse. They are going to accept the electrons from the carbon-halogen bond onto themselves, and then they are going to leave. So we have to have something that is going to form a stable negative charge with those electrons that it's removing. We can think of this kind of in terms of weak acids and bases. Good leaving groups tend to be good weak bases, because when we think about a weak base, we think about a protonated A-, if we like, and we think about the equilibrium and how much that lies to the right-hand side. The more that equilibrium lies to the right-hand side, the more we have a good weak base, the products in the dissociation of the weak acid. So the conjugate base, if that is a good weak base, then we are going to have a good leaving group. We can even frame that in terms of the pKa. The more stable it is to the right-hand side, the higher the concentration of H+ we have, and the higher concentration of H+ we have, that means that we're going to have a lower value of the negative log of pH, so the pKa will be lower for good leaving groups. We can also put this in terms of the size of the atom, because as a rule, the larger the atom, as in iodine, bromine, and chlorine we have in that position, the better the leaving group. And that makes sense because the distance of the outer electrons to the nucleus, as we've done in previous units, is going to be further away, so that carbon-halogen bond is going to be weaker, which reiterates the point that we just made about the pKa value. The last thing we're going to look at is how the nucleophile can affect the mechanism and the rate. Now, there are 4 different components to how this can happen: through charge, electronegativity, the solvent, and steric hindrance. Now we're going to focus mainly on charge, although I will mention how the others also affect the rate. Hopefully you might have some idea how charge can affect nucleophilicity. As we know that nucleophile, nuclear loving, it is electrons that drive this attraction to positive charge, so it's no surprise that the larger formal charge we have, then the higher the nucleophilicity, because there are more electrons available. We can illustrate this with water. Water works as a good nucleophile. It has lone pairs. However, if we remove a proton, we make the conjugate base with a formal charge, the OH is going to be a much stronger nucleophile, which is probably what we'd expect because we have a formal negative charge. Indeed, it's true for all nucleophiles that the conjugate base is going to act as a stronger nucleophile because we've removed a proton. By removing the proton, we're increasing the number of electrons and therefore increasing the attraction to any positive charge centers, which is what a nucleophile does best. So there are other factors that affect the nucleophilicity. These are electronegativity, solvent, and steric hindrance. These are not as important, and we're just going to cover them very quickly here as an overview. Firstly, that nucleophilicity decreases with increasing electronegativity. This would make sense because as we increase the electronegativity, that is going to be less likely to give up those electrons to participate in a reaction. Hydrogen bonding in the solvent, which we already looked at a little bit in the mechanism, but also hydrogen bonding in the solvent inverts nucleophilicity. This can be a little bit confusing to think of, but in polar protic solvents, we have iodine is the best nucleophile of the halogens, and in polar aprotic solvents, we have fluorine being the best, things like acetone. So we've kind of focused on this order, including H-bonding solvents. Nucleophilicity is decreased with steric hindrance. This makes sense. The more baggage these things are carrying around, the less mobile they're going to be able to be, and as a nucleophile attacks, the larger these groups, the less strong of a nucleophile it would be, as demonstrated with these examples. However, for these factors of the nucleophile, I would suggest only remembering these almost as a list of things that can change the nucleophile, not going into any depth. A couple of questions then before we get started on the nucleophiles. Why does steric hindrance favour SN2 reactions? Pause the video. Pop 'em up! Remember, in an SN2 reaction, the nucleophile needs to attack the electron deficient carbon that's bonded to the halogen or leaving group, and because of that backside attack, the less things in its way, the more easy that attack will be, and the more successful the SN2 process could be. So the more R groups there are, the more there is blocking this attack. Indeed, the larger these R groups are, the more they will further block the attack of the nucleophile. Next, which reaction would you expect this compound to undergo with aqueous sodium hydroxide, and draw the product? Pause the video here. Pop 'em up! So in this compound here, we have a tertiary halogenoalkane. That means we're going to have lots of stabilizing groups if the bromine was to leave us an intermediate carbocation. So we're going to favor that formation because of the positive inductive effect, and therefore it looks as though we're going to have an SN1 reaction, which is going to form our tertiary alcohol. Next, which of these two compounds would you expect to undergo nucleophilic substitution at a faster rate, with all other things kept constant? Pause the video to have a go at this. Pop 'em up! So both of these molecules are tertiary, so we're going to look at the leaving group. We've got bromine versus iodine. We know iodine is larger and has that lower pKa value and is a better leaving group, therefore signifying it would want to break that bond more easily and undergo an SN1 reaction more easily, increasing the rate of reaction. So far, we've really only looked at having OH- as a nucleophile, or water, mainly OH-. And so what we want to do is we want to broaden the nucleophiles that we can use and look at a couple of specific reactions. The two we're going to look at are going to be ammonia, that's NH3, and the cyanide ion, that's Cn-. Firstly, let's consider the case of ammonia. The conditions for this reaction is we're going to heat this under reflux at a constant pressure, and we're going to need to have obviously some halogenoalkane. So we're going to have an overall reaction of any given halogenoalkane, so in this case bromoethane, plus 2 moles of ammonia. That's really key, the 2 moles of ammonia. I'm going to come to why that is soon. And we end with the primary amine and NH4Br. Let's have a look at the mechanism. It's going to be very similar to what we already know, except instead of OH-, we're going to have the backside attack, in this case, going from the lone pair on the N of the NH3, forming our intermediate. Now, it's not going to be an intermediate anion because the nucleophile itself doesn't have a negative charge, but we can consider the nitrogen that is now bonding as having a positive charge itself. So our product of that step is actually another intermediate. After the bromine leaves, we now get this cation. And this is exactly why we need another mole of ammonia, because we want that ammonia to actually come and pick up one of these hydrogens on this positively charged intermediate. The lone pair will come by, pick up one of these hydrogens, and then the electrons from that will go down onto the hydrogen, forming our primary amine and some NH4. That NH4 will, of course, be able to bond with the leftover Br- from the first step of the reaction, forming that NH4Br. So far, so good, but there is still one thing we need to consider, and that's with the actual product of this reaction, our primary amine. And this is a real key point and why ammonia is used in excess in these reactions. Indeed, the primary amine that we have produced itself can act as a nucleophile because it still has that lone pair. So here's our product from this reaction that we just went through, and you can see we've got the lone pair. Now, what can happen is if ammonia starts to run low, and let's draw out our halogenoalkane here, if our product starts to run low, then the actual product of the reaction can start to act as a nucleophile itself and begin to attack that electron deficient carbon attached to the halogen again. If we think of that as our second reaction, we can write out the overall equation for that as our primary amine plus more of the halogenoalkane is going to substitute in and form a secondary amine. We're actually going to add another ethyl group in place of one of the hydrogens. And of course, we're also going to still have produced another nucleophile. So again, we can add that product can still act as a nucleophile if we're running low on ammonia and react with more of the halogenoalkane. And if you are perceptive to the trend, what can happen with this? Well, this is still a nucleophile. Indeed, this is the worst case scenario. We can form the quaternary salt where we get this tertiary amine reacts again with the halogenoalkane, forms the quaternary ion, and then that bonds with the bromine, and we don't want this to happen. This is the quaternary salt. So this is why we need to have lots of excess ammonia because based on what we did earlier in the video, we know that less steric hindrance makes ammonia a stronger nucleophile than the primary, secondary, or tertiary amines produced. So as long as we have enough ammonia around, it will preferentially take part in the reaction, producing the product that we want. Please be aware that you don't need to draw the mechanisms for all of the stages of this reaction, although it can be a good revision exercise to go through because you're going to end up with some large molecules and it's going to look pretty ugly, but still good practice if you would like to try it. But you do need to be able to write out these equations that show the secondary, tertiary, and quaternary substitutions of the amine. Turning our attention now to the cyanide ion, which follows the reactivity a lot more similarly to the nucleophile of OH-, but here we're really going to focus on the significance of this reaction. What it actually does to the molecule is something that you just have to make sure you're switched on to. So the conditions for this reaction are going to be aqueous solution of any salt of cyanide in an alcoholic solution. So it's going to be kind of an ethanol water mixture with the salt dissolved and some halogenoalkane in there as well. An example overall reaction, if we take the same bromoethane that we used in the last reaction, we're going to swap out the bromine for this CN double bond. And the significance here is that we have bromoethane, a 2-carbon molecule, coming into the 3-carbon chain cyanide molecule. And that is significant because we are extending the carbon chain. Very powerful organic chemist's technique here. If we have a look at the mechanism though, it's very, very simple. We're just going to have the cyanide ion is going to attack the electron deficient carbon. That's going to cause the bromine to jump off, again forming our transition state intermediate. Now this will be an anion transition state because we have the cyanide anion. And then the bromine, as always, will be the leaving group, which will leave us the 3-carbon chain product molecule. So hopefully there, nothing too major in terms of the mechanism. This mechanism is exactly the same as the others. What we do need to know is 2 reactions that we do with the nitrile once we've formed it. Nitriles aren't usually our target molecule, so we can hydrolyze this by reacting it with water to form carboxylic acid and some ammonia. We can also reduce this by reacting it with some reducing agent, and that is going to form the primary amine by adding the hydrogens onto the nitrile. We will use a platinum catalyst for that second reaction, and once again, you don't need to know the mechanisms for these 2 reactions, but you do need to be able to recognize that you can do these reactions and the products that would be formed in a larger scheme, but we will cover that more later in the unit. Okay, couple of questions then to round off the video. Firstly, have a go at drawing the mechanism for this reaction. Pause the video to have a go at that. Pop them up. So here, hopefully we notice that this is actually exactly the same reaction as I just used as an example because I'm that lazy. The electron deficient carbon. And in this case, because we have the primary halogenoalkane, we would get the SN2 reaction. So we're going to get our intermediate transition state. Remember, this is not going to be an anion, but we are going to then produce a further intermediate, which is going to be our cation with our positive charge on our NH3 group. And then the hydrogen, or one of the hydrogens that is attached to that group, will be picked up by the excess ammonia that we have, the other mole of ammonia, and then the electrons that are in the bond to that hydrogen will then go down onto the nitrogen, reforming the lone pair on the nitrogen, which will give us our product of our primary amine. And then that NH4 that we've produced will bond with the Br- that will be produced from the first step of the reaction. Don't make the same mistake I have here in the first step of the reaction and not draw the arrow that shows the electrons going from the bond between the carbon and the bromine onto the bromine before it leaves. Make sure you include that. Last question then, draw the reactants and the mechanism that forms these products. Pause the video to have a go at that. Pop them up! Breaking the molecule and the question down, we can see we've got a 4-carbon chain, but one of it's coming from a nitrile, and we've got the KBr. So we know we're going to have the cyanide ion that would have been the reactant, and we know we're going to have a halogenoalkane, which has 3 carbons. And we can see that because we have KBr, that the halogen in question must have been bromine. Then we just do our regular old substitution. Here, it's going to be an SN2 reaction because we've got another primary halogenoalkane, so we form another intermediate anion, and it is an anion this time because Cn is negatively charged, then forms both products that they gave us in the question. So, no other videos to go with this one. There are some questions for you to be getting on with, and practice is going to be key to this, guys. Once again, thanks for joining me. Make sure you like, subscribe, share the video, and as always, practice makes slightly better.